So let's look at this example. Is this sequence 2 times n over n plus 3, is it convergent? Well, let's just play around with this example for a second. I'm going to have the computer compute the first 4 terms of the sequence. So we see the first 4 terms are a half, 0.8, 1, 1.14, etc. Do these numbers seem to be settling down anywhere? Well, maybe 4 terms isn't enough. Let's try 100 terms. So let's scan down the list. So we're at around 1.4, 1.5, 1.7, now we're at 1.8. Still hovering around 1.8. Now we're into 1.9. It looks like for the last 40 terms of the sequence, we're hovering around 1.9, slowly increasing that next digit from 3 to 4. Does this give us an idea of where the terms of the sequence seem to go? Well, it seems to suggest that maybe they're heading towards 2, but I don't know. They might pop past 2. Eventually, they might pop past 2 and head somewhere else. But, you know, this is the idea. These terms of these sequences, they're heading somewhere, perhaps. Can we figure out where they're heading? And for this particular example, we can. So one way to do that is to rewrite the example as 2 times n plus 3 on the top. And now I've actually artificially inserted a 6 on the top, so I'm going to take it away as well. So now I've just rewritten 2 times n in a fancy way. And I've done this because now I can divide n plus 3 into both. And the key here is to notice that, well, wait a minute, an, being terms of a sequence, they're just function values. So notice that an are just the function values f of n for the function f of x equal to 2 minus 6 over x plus 3. Okay, it may not look like we've done much with writing the statement, but in fact we have. So what I've done is I've said, hey, wait a minute, these terms of this sequence actually live on this function. And now I've converted the problem of computing the limit as n goes to infinity of an to the question of computing the limit as x goes to infinity of f of x. Because the terms live on this function f of x, so they must go the same place that the function goes as x goes to infinity. And now we can use our results of how to compute limits from Calculus 1. So this becomes 2 minus 6 over x plus 3. We notice that x gets big. This 6 over x plus 3 goes to 0, so the result is 2. And so there is the limiting value of our sequence. So an converges to 2. And this idea of imagining the terms of a sequence as living on a function is so important that we state it as a theorem. So consider the sequence, which is given by function values f of n. If the limit of the function is L, as x goes to infinity, then the limit of the sequence must be L. And the diagram indicates why. So the terms of our sequence are these dots. They're living on that function, and I know where the function goes. I know the values on the function head towards this line L. Then the terms of my sequence, which is bound to that function, must also go to L. So this implies that we have a whole host of results about computing limits of functions that we can now apply to computing limits of sequences. And so we state these results in this box, which I've called facts about sequences. And all these things say are just that the properties that we had for limits of functions just translate over directly to limits of sequences. So the limit of a sum or difference of sequences is the sum or difference of their limits. And so on all the way down the list. There's a few things we need to be careful of. If I'm looking at the limiting value of the ratio of 2 sequences, I just need to make sure that the denominator doesn't go to 0, because otherwise I'll be dividing by 0. The limit of a power of a sequence is the power of the limiting values. This is an interesting one. Sort of looks innocuous at first, but it actually turns out to be quite important for us, and we'll see an example of it in a little bit. If I know the limiting value of the absolute value of the sequence, and that goes to 0, so the magnitude of the terms of my sequence are getting small, then the values of my sequence themselves must be getting small. What about if the terms of my sequence Cn are bound between 2 other sequences? For every n, Cn is trapped between An and Bn. And I know that An and Bn as sequences go to L. Then the one trapped between them must also go to L. And this carries directly over from a result from functions, which was known as the squeeze theorem. And if an is a sequence that goes to L, and f is a continuous function at L, then applying f to all the terms of my sequence, the limiting value of that is just f of L. So in some sense you can think of this as just popping the limit inside the function and evaluating the limit of the an first before you evaluate the function. Okay, I skipped over the definition above, and this is just an extension of one that we already knew from functions. We define the limit as n goes to infinity of an to be infinite if for every big M, so for every big M, this we imagine to be the values of the sequence, there is some index, little n, so that if you go out far enough, say from a sub n onwards, then each of these things is bigger than m. And if this is true for every m, no matter how big you choose m, you can go far enough down the sequence so that everything beyond that point is bigger than m, then you know your sequence has to go to infinity. It's got to blow up. It can't be bounded by anything. It's got to blow up. And in that case, we write that the limit of this sequence goes to infinity. So let's look at some examples. Show that the sequence, the nth root of n, converges to 1. I'm just going to have the computer calculate a bunch of values to see if we can spot a pattern. This isn't necessary, of course. We'll see that we can find these limiting values in other ways, but we're still building an intuition up for what it is we're actually doing in this section. So let's have the computer crank out a bunch of values, and let's just look. So here's the terms of our sequence down the column on the right. And so we're at 1.3, 1.2, 1.1, 1.1, 1.0, 1.07, 0.6. So it seems to be we're dropping. Our values are dropping. 1.04. So again, scanning back up from the beginning, we start at 1.4 and we drop all the way down to 1.04. So we seem to be getting closer and closer to 1. But we don't know for certain. That's the point about these tables of values. When we crank out a bunch of calculations, this in no way tells us what's happening, at the thousandth term or the millionth term. Maybe it does drop past 1. Maybe it's actually on its way to 0 and we just don't see it yet. So the point is that this can give us some information about what's going on with the terms, but it doesn't give us any conclusive results about where these terms actually go very far off. So that's where we're going to need to actually compute the limit of this thing. So consider the function that this sequence lives on. So we can write that as x to the 1 over x. And let's suppose that the limit exists. So suppose that the limit as x goes to infinity of x to the 1 over x equal to L. Our goal is to try to figure out what L is. Now the reason I've done this, I've written it equal to L rather than just tried to go ahead and compute what this limit is because this one is a limit that when we studied it in Calculus 1, we saw a function raised to the power of another function. We can use logarithms to drop the power down, so to write it as a product. And so I'm going to use the technique of hitting this with a logarithm in order to compute the limit. And in order to do that, I should have what the limit is equal to on the right-hand side, so I get an equation that I'm working with the whole time. So I'm going to hit logarithms to both sides. And when I hit logarithms to both sides, well, logarithms are continuous on their domain, so I can swap the limit and the log, and log of x to the 1 over x, the 1 over x comes out front, so that I can write as a 1 over x times ln of x, and then the other side is ln of L. And I can rewrite this then as the limit as x goes to infinity of ln of x over x, and that's equal to ln of L. So our goal is to try to figure out what L is, but now we've got an equation that it has to satisfy. And the reason we're using logs again is to not have to worry about dealing with exponents. Instead, now I'm dealing with a product. And now I've got as x goes to infinity, log of x, this goes to infinity. The thing on the bottom goes to infinity. So this limit is of type infinity over infinity, and that's a typical case of where we would use L'Hopital's rule. So L'Hopital's rule says take the derivative of the top, put it over the derivative of the bottom. This limit, whatever it is, it's also got to equal this limit, whatever it is. And both of them have to equal then ln of L. And now the limit as x goes to infinity of 1 over x is 0. And that's what ln of L is supposed to be, so that tells me that L has to be e to the 0 or 1. And so our observations from that table of values that we cranked out, where it looked like the numbers were going to 1, we still didn't know from the table of values if they actually passed 1 and continued on down to 0 and maybe off to some other value. We now have conclusively that those numbers are indeed heading towards 1. And we got that by computing the limit, and in this case, using L'Hopital's rule. So let's look at the next example. Is the sequence sine of n pi by 2 convergent or divergent? Well, let's look at a few terms of the sequence. When n equals 1, that's sine of pi by 2, which is 1. When n equals 2, that's sine of pi, which is 0. When n equals 3, that's sine of 3 pi by 2, which is negative 1. And when n equals 4, that's sine of 2 pi, which is 0. And then we just seem to be going around. I'm looking at the unit circle here, and these angles, these multiples of pi by 2, are really just picking off these points on the unit circle. And so our terms of our sequence are just going to be the y values. So we go 1, 0, negative 1, 0, 1, 0, negative 1, 0. And so this thing repeats. So the question is, does the sequence converge? Do those numbers head towards a particular number? Do they get closer and closer and closer to some fixed number? And the answer is no. They bounce around. They go from 1 to 0 to negative 1 to 0 to 1 to 0 to negative 1 to 0. So this sequence does not converge. And so therefore, it diverges. That's the definition of diverges. It means it doesn't converge. So these terms in this sequence diverge.